Hello, my name is Niklas. I'm from PDC, the High Performance Computing Center at KTH. I'm going to present a paper, a hybrid MPI+PGAS approach to improve strong scalability limits of finite element solvers. As we all know, we soon have exascale systems reaching billions of parallel activities. And if we want to use them efficiently, we either need unreasonable large problem sizes, or we have to investigate time to design more scalable algorithms, both from a numeric and a computer science perspective. For industrial problems, we often have unstructured meshes. Although they're great to approximate complex geometries, it's very challenging to create these large meshes necessary to fill an exascale machine. And they also come with very irregular communication pattern that might be difficult to scale in a strong sense. So in this paper, we developed new methods that will be able to scale strongly with fewer grid points per processing element. So the main focus is finite element simulations, where we have basically two costly operations. One is to assemble the linear system, creating a large sparse matrix, and secondly, solving this system. So consider the flow past an aircraft here. Looking at the performance data at the bottom, we see that it scales to around 30,000 grid points per core. What we want to do is to reduce this even further, such that we can take this problem and run it on an even larger number of cores. And looking at the figure to the right, we see that assembly actually loses strong scalability already at 1,000 processing element. So that is the starting point. Starting very basic, we look at if we can improve the sparse matrix format. And we all know that compressed sparse row is good for sparse matrix vector multiplication, although assembly might be costly unless you have pre-allocated it with all the non-zeros. So instead, we're considering using a stack-based format, where each row in the matrix is represented by a stack or a list holding tuples of column index and value. So inserting new data into the matrix is basically for free. You just push a tuple to the corresponding list and you're done. These are not sorted. The problem here is that the SPMV performance is then lower than CSR. But for most engineering simulations, the sparsity pattern is static. So after initial assembly, we can rearrange all the row stack into consecutive memory locations and then retain the same CSR like SPMV performance. And the parallelization, what the costly here comes from other sources. So when we want to assemble a matrix in parallel or in serial, we loop over all the elements in the mesh. And for all the basis function combinations, I and J, we add the corresponding contribution from the element stiffness matrix into the global matrix A, using a mapping function capital I that will map to a global row and column. So in parallel, A is distributed by rows. So each processing element has a continuous set of rows. And so the assembly is then done in a two-phase process. So first, if capital I will give you a local row that is owned by the current rank, you insert the data directly. If the mapping function gives you a non-local row, it will be placed in a buffer. And once each MPI rank or thread has assembled all the local elements, they will exchange the buffers with each other in the final step and insert it into the matrix. And again, all the threads will not talk to each other. This is a completely unstructured exchange of messages. And furthermore, if you implement this using two-sided message passing, basically MPI, you will have a lot of message matching, which might drive up your latency cost. And if you do the profiling, you see that is exactly why the assembly of the pressure matrix here stops to scale. So computing the element integral is basically for free. So it's basically you against the network pushing data into the matrix. That's why you lose the scalability so early. So you consider changing the one-sided communication, and the first thing you think about is using MPI remote memory. Although you start reading specification, this was back in the MPI 2.0 days, and we realized, no, there are too many restrictions. We cannot really use them for the things we want to do. So instead, we looked at PGAS languages. So the family of partitioned global address space languages offers you a true single global address space. So any thread may directly read or write at any remote memory location concurrently. And also the memory is partitioned such that each thread has affinity to one part. And we have several different flavors of the languages. We have Cray Fortran, we have SPMV, Chapel, and Unified Parallel C. And UPC is the choice for our implementation here. So for those of you who have done programming UPC, you know that you have this UPC style arrays. they're distributed by blocks across all threads. So it's very easy to access data on any thread by just saying both I, and I can be the same number on all threads. It's the global index of the array. The problem is that you have to allocate this with a fixed block size of n for all threads. So basically, your problem size must be divisible by the number of threads. So if you think of this in a sparse matrix sense, it means that we need to have a number of rows per thread that is divisible, which seldom is going to be the case with unstructured matrices. So instead we use the director of objects approach. So we don't allocate the final array in the global memory, we allocate a director in global memory, and then we also then, for each entry, we allocate a local buffer, still in global memory, which has affinity to a certain thread. And so these local buffers can then grow and shrink completely independently of each other, and we can still access them from any thread by traversing the directory. So what we try here is to improve the performance of Dolphin HPC, which is the HPC branch of the FEniCS project's finite element framework Dolphin, which has a hybrid parallelization. We usually say it is MPI+X, so today X will be PGAS. And the path forward here is then to say that we have a legacy MPI code. We see that we have scalability issue due to latencies induced by MPI. And often one will say, no, it's too costly to rewrite a large code base. But we're going to demonstrate here is that we can rewrite a latency sensitive part of it in PGAS and improve performance of the entire package. So what we have done is to develop a sparse matrix library written in UPC, and it serves as a drop-in replacement for the current linear algebra backend. So basically we have a situation to the right that Dolphin and FEniCS run completely in MPI, doing mesh partitioning and evaluation of finite elements. And only the linear algebra part is running in UPC. And this is completely transparent to the user. They just change a switch inside the code to use a UPC backend instead of an MPI-based backend. And the final thing to solve in order to run this is actually be able to run MPI and PGAS. So mixing these kind of languages has always been a cause of headache. Dolphin is written in C++, which works perfectly fine together with C. UPC extends C99 with shared pointers, which means you cannot link it with C++. So instead we use an old technique of opaque objects. So on the UPC side, we have our normal structs with shared pointers incompatible with C++. So on the C++ side, we instead said to Dolphin, look, you have a chunk of memory A here, just pass it down to the sparse matrix library and be happy. So you cannot modify the data on the C++ side, but you can have the data on the C++ side. So everything is done inside the UPC side. So to evaluate the feasibility of this approach, we started with a sparse matrix assembly benchmark. So we tried 4 different problems, 4 different equations with various characteristics and problem sizes. And we computed the finite element integrals inside Dolphin, and then compare the reassembly time using 2 different linear algebra backends. First, the default PETSI, which is the default MPI backend in Dolphin, and then our new UPC-based backend. So as I said, we only measured reassembly time, so this pre-allocation in the beginning for CSR is completely removed. And we tried to do this 100 times, and then took the average of the reassembly time. So this was run on a Cray XC40 Hornet at HRS using the Cray compiler version 8.6. And Cray compiler has shown to be one of the best compilers for this kind of mixed MPI-PGAS work. So looking at the results, we clearly see that benchmark A and C shows significantly improvement in terms of scalability compared to the MPI-based backend. And the reason for this is that both A and C, so we're starting with A has a very inexpensive equation. It's just Poisson equation. So it's very inexpensive to compute. So it's similar to what we saw in the beginning, is U against the network, just pushing data. So here, once we have few elements per core, we have increased latency cost of message matching using MPI, and the scalability stops completely, while we continue to scale well using UPC with the one-sided communication. For benchmark C, it's linear elasticity, so it's a more costly equation to assemble, but in this case, we have as few as 500 elements per rank at the end, and we still scales well due to the one-sided communication. B and D, we don't see a clear benefit of UPC because they are more balanced in terms of computation and communication, but we see a certain performance gain of using UPC due to our new sparse matrix format. This is very encouraging, so the next step to actually run a full problem is to implement the solvers. And all the solvers, as I mentioned, are iterative methods in finite elements. So there are Krylov solvers, which needs a very good SPMV kernels. So in parallel, we are distributed matrix by row, which means that we need to fetch entries from the vector x, which is also distributed by the same rows as the matrix. So for example, rank 0 needs to fetch the green and the pink from 1 and 2, for example, to perform that part of the matrix vector multiplication. So to optimize this further, we subdivide the matrix into blocks. So we start with the diagonals here. And of course, this part corresponds to complete local data of x. So we don't need to do any communication to compute this part. And the second red part here is then the off-diagonal part, where we need to do communication of x to fetch the dependencies. So in the end, you have a distributed SPMV using message passing. So first you initiate the synchronous messages to fetch data from x using MPI I send I receive. While you're waiting for messages to arrive, you compute the local part, and then you do synchronization, and then you add the data you received into the final result. What's very important here is that we need to actually implement number 3 in UPC. We need to do some synchronization. And since it's an unstructured mesh, it's actually coming down to point-to-point synchronization of these matrix dependencies. So MPI provides this directly implicitly via the send and receive, or rather the two-sided aspect has this implicitly that you have to match send and receive. For PGAS, you need some kind of signal and functionality that you signal the receiver that you have put data in its memory space. Some PGAS languages implements this, UPC doesn't. The only thing we can do in UPC is either to have barriers, which will over-synchronize everything, or we can use UPC locks, but experiment has shown that these are quite expensive. It has a high latency of acquiring the locks. And the last option is to use strict variables. So we can basically implement our own synchronization primitives by having semaphore-like variables that we can then poll until a correct signal has been raised by another thread on these variables. So using this, and also given the thing that we have to be able to receive data from an arbitrary number of neighbors concurrently, we cannot use the directory of objects approach as for the matrix. So instead, we extend this to a directory of directories of objects approach. So each thread can then actually receive data from all the neighbors concurrently. And of course, this will be very expensive to allocate in memory, so we only build the full directories and the buffers for our neighbors. And we build a similar structure for the synchronization primitives that is marking if buffers are free or containing data. And using this construct, we can create a sparse matrix algorithm in UPC following the same principle as message passing. First, initiate communication. Secondly, compute the local part. Third is synchronize the communication, and then add the received part into the sparse matrix product result. So first, starting off with the first initiator communication. So basically, we have 3 different sets. So S is just empty in the beginning. Q is all the threads we're going to receive data from. And D are all the threads that I own data for that I have to send to them. So as a start, we check if the remote buffers are ready for me to send data. So I will try to put my dependency I own to the one who wants it. So this is a shared memory polling. We're polling a remote place in the directory of directories. So basically, for example, if we want to send from 1 to 3, we traverse from the global directory into the directory on his address space and check if the buffer is ready. If it is ready, we issue a asynchronous memput and store the handle locally so that we can synchronize it later on. We then perform our local part of the matrix, vector multiplication, and then want to synchronize everything. And now the final synchronization is done if all the data we asynchronously put has been received, and we also have received all the data we expect from our neighbors. So S was the set of all neighbors we have asynchronously initiated a memput to. So first we check if the memory has been transferred completely. And if so, we then signal the receiver by marking the corresponding synchronization primitive flag in his sync structure that now we have data. And of course, at the same time, a receiver will also check if data has been received. If it has been received, you reduce how many neighbors you expect data from, and you continue to do this until everything is in place, and then you perform the local part of the sparse matrix vector product with the received data. An important thing is that one might think it's quite costly to spin and wait until you have received data, but the important part here is that the way this is constructed is that you spin on the local part of the sync structure, so everything is in your part of the global address space with affinity to your thread. So it's not as costly as spinning across the network. Which means that basically we have all the tools necessary to run a large flow case. So we have used an incompressible flow solver built on top of Dolphin HPC at an implicit time stepping, so which means that you have to assemble 2 matrices in each time step, and you have to solve 2 systems. So we try here the performance for 2 different cases. One is a 6 million element mesh, and the other one is a 190 element mesh to see if we get some different scaling characteristics. This was also run on a Cray XC40, this time BESCO at PTC at KTH, and using Cray compiler version 9. And now again we compare against the time against pure MPI using PETSI against our new UPC-based backend. And we measure the average time for assembling the continuity matrix and to solve the pressure problem. And we measure this once the flow has developed, such that the fixed point will converge in 1 or 2 iterations. Compared to the sparse matrix assembly, we don't see a clear benefit of using UPC here. However, the positive thing is that if you look at the results for the Krylov solvers to the right, one might think that our elaborate sync structure might be expensive, but we see that it performs on par with normal non-blocking MPI ICE and IRC, which is good news. And to the left, we see the matrix assembly. Again, we see that it's slightly faster than the MPI due to our sparse matrix format, but we don't see the clear benefit from the lower latency one-sided communication here. And the reason for that is that now we have a lot of more terms, so we have a more balanced problem compared to previous Laplace equation that scaled very nice. So to summarize, the feasibility of the hybrid MPI+PGAS approach. So you can see large performance impact for communication-bound problems, significantly improving strong scalability limits. For more balanced problems, you will not see a large impact. However, communication isn't anything here. Having part of the code in PGAS will allow you to formulate new algorithms that previously deemed impossible due to very challenging data dependencies and the MPI two-sided message passing model. So future work here is that we acknowledge that UPC is a language, it needs a compiler. It has a very good support on Cray platforms. Other platforms, not so much. So we have started to investigate the feasibility of using UPC++, which is a C library with better support on various platforms. And finally, I want to acknowledge the funding from the Swedish Research Council and the European Commission, the Horizon 2020 project, Accelerate as well. Thank you for the attention.